One simple idea that can make universal good algorithm is introducing regularization, like RW function for this follow the reader rule. Okay, so basically the follow the reader rule that does not have RW function, but it just minimize the sum of rows function. Okay, the follow the regularized reader rule includes RW function. Again, R function is also convex usually, and then optimize not only the not just the sum of rows function, but the sum of rows function plus the regularization function. Okay, so this regularized approach is very common approach in machine learning. For instance, the lasso or Ritchie regression, both are very famous approach for regression task. Okay, lasso regression basically introduces L1 um, additional regularization term, and Ritchie regression introduce L2 cost function, L2 regularization term, so that our learned parameter becomes more regularized, and that basically reduce the generalization error, the difference between training error and test error. Here again, when we introduce such additional regularization term, we can expect kind of similar effect. We can expect the trajectory WT becomes more stabilized, and which can make our loss more stable and more less than before. For instance, in the previous case, we can freely go between +1 and -1. So every time slot we change our decision +1 and -1 all the time. But if we introduce additional regularization term like RW, the RW can, enforce the such movement +1, -1, +1, -1 stay near 0. So it can make a +001, -001, and so on. Okay, we can restrict the difference between two consecutive time slots using the R function regularization term that can fix at least this example. Okay, let's see more rigorous and detailed proof for an algorithm that follow the regularized reader algorithm. The regret of follow the regularized reader rule is upper bounded by the regularization value RW star at the optimal point W star minus RW1, the regularization function value at time 1, plus summation from T1 to capital T, FTWT minus FTWT plus 1. So this term exactly the same with the FTL rule, and we additionally have this term. So if we don't think very carefully, maybe we can think this upper bound is worse than the previous upper bound because we have additional term. But that's wrong. Why? Due to this additional regularized term, we change the sequence WT, and the updated algorithm, the FOLEL, can make this term much less than before. Right. So let's see the proof and let's see the example. So the proof is very simple. When we set f0, so let's assume the algorithm not start from f1 function, but start from f0 function with just pure regularized function r with arbitrary starting point w0. Then from the previous lemma, previous result, we have that the regret of ft is upper bounded by rw star minus rw0 plus summation t0 to capital T ft double t minus ft double t plus 1. Why we have this term? So this regret from the definition is just simply t1 to capital T ft wt minus ft w star. So there is no room for rw star minus rw0. So t equal to 0 term move from left hand side to right hand side. That is rw star minus rw0. Okay, to use previous lemma, this left hand side should start from t0 and end at capital T. But the definition of regret should start from t equal to 1. So we have to remove t equal to 0 term from the left hand side. So we move t equal to 0 term from left hand side to the right hand side. That is rw star minus rw0. And then when you bring out t equal to 0 term of this summation, then we have this, right? So this lemma is very easy to show. So let's see some example with very simple additional regularization term Rw. Let's consider L2 regularizer like 1/2 eta. Eta is kind of running rate or step size times W norm square. That is very famous regularizer. So when we consider linear loss function, as in the counter example, failure of FTL, then with any z 1 to z capital T, we can show sublinear regret. So we can say that this regularizer solved the exploding regret issue. Okay, why? So from the regularizer, we have this wt plus 1 is not just optimize the ft function, the wt plus 1 not just optimize ft or sum of ft. Instead, because of this regularizer, we have cumulative information of gt value, sum of gt from, sum of zi from i1 to t. Okay, in other words, when we start from 0 vector, we have wt plus 1 is equal to wt minus eta zt. Okay, this is kind of gradient descent. Why? Here, the gradient of loss function with respect to w is just zi. So every time step, we move to the negative direction of gradient with step size eta. When we introduce this additional regularization term Rw. Okay. And since every ft is convex, for any other general f function, we have this inequality, right? We have this inequality. So I just use the definition of convex fi wi minus fi u is upper bounded by gradient of the inner product between gradient of fi wi and wi minus u. That holds because fi is convex. Every f is convex, we have this. So when we set f tilde I is equal to the inner product between gradient of fi wi and x, sorry, this is w, then we have this. The max of summation t equal to 1 to capital T ft double t minus ft u is upper bounded by max summation t equal to 1 to capital T f tilde t double t minus f tilde t u. Why? Because of this inequality and because of the definition of f tilde I. Here I just rewrite the inequality using f tilde. Okay? And since this inequality holds for every u, we can put the max sign here. Okay? So for any cost function, any loss function ft, when we learn for an algorithm for f tilde t, then we have this gradient descent rule, or it is called all-line gradient descent rule, because every time f function is updated, then what will happen? So before going to the result, let's define more general version of all-line gradient descent algorithm. We start from parameter step size eta and initial point 0. At every time step, we predict wt and then receive zt, and then we can compute vt, the gradient or subgradient at point wt, and then update our parameter value using gradient descent rule. So this is wt minus step size times gradient vector. And then when the wt plus 1/2, why this is 1/2? For the case this updated position is outside of our constraint set hypothesis class H. If our updated parameter w becomes outside of hypothesis class H, then we have to project the outside data point to the inside of our hypothesis class. That is this. We compute these argument operations. So we basically find the point inside hypothesis class that having the minimum distance to the wt plus 1/2. Okay, so when we have this limited space, and from wt, if our wt plus 1 go outside, in this is wt plus 1/2, we have to project this point to this boundary. Okay, that is wt plus 1. Okay, so again, when we have some constraint set, then the simple gradient descent rule can be outside of constraint set. So every time we have to learn the projection operation as well, so that the trajectory becomes inside of our constraint set. Okay, this more general all-line gradient descent rule has this theoretical result. The regret is upper bounded by w star normed square over 2 eta. Here eta is the step size, learning rate of the GD rule. plus eta over 2 times summation t1 to capital T vt norm square. So here vt is the gradient. So gradient norm square. Okay. So roughly when we set eta is equal to 1 over square root of t, this, and if f is some Lipschitz continuous function every time t, then we can upper bound vt norm square by rho square. So we have this very nice regret. Some constants times square root of t. If we further assume that our hypothesis class is bounded, then W star also bounded. So using this, we can more tighten the bound using more tighten step size eta equal to b over rho times square root of t. Then the regret is upper bounded by b times rho times square root of t. Here b is bounded constant and rho is Lipschitz constant. Okay. And since this is very general result, this result includes the case this as well, right? When we follow the reader rule using this L2 norm square regularization function, the update rule follow O-line gradient descent rule. And this O-line gradient descent rule guarantee square root of t regret growth with respect to time t. Okay, so it looks like our additional regularization term L2 norm square looks like very nice. So how to show this? So the proof strategy is very simple. We first upper bound the norm square of wt plus 1 minus w star minus the norm square of wt minus w star, and then we will sum over t. Then we will have the result. Okay, so we can rewrite this by adding same term and subtracting same term. Okay, and since wt plus 1 is the projected point of wt plus 1 half. From the definition of projection, we know this. Wt plus 1 minus w star. No, this is less than or equal to wt plus 1 half plus w star. Because w star is inside of our hypothesis class. So using this fact, we can erase this term. So we can upper bound this term by 0. Okay, so this is upper bounded by wt plus 1 half minus w star norm square minus wt minus w star norm square. From the definition of O-line gradient descent and the wt plus 1 half, we can rewrite this term by wt minus eta vt. And since the norm square is inner product between the same vector, so when we use that fact, then we can rewrite this subtraction like this. Minus 2 eta times the inner product between wt minus w star and vt plus eta square vt square. Right. And from the fact that ft is convex and vt is subgradient of ft at point wt, we can rewrite, or we can upper bound this term by minus 2 eta ftwt minus ftw star. Okay, so we have very nice upper bound of this term, and so when we summing over t this, then we can subtract And in the end, we have the normed square wt plus 1 minus w star minus the normed square of w1 minus w star, which is upper bounded by minus 2 eta summation from t1 to capital T ftwt minus ftw star plus eta square t1 to capital T vt square. So rearranging the inequality, we have regret is upper bounded by w1 minus w star square minus something, but because this is positive thing, we can simply ignore this and upper bounding this term, so which is upper bounded by w star normed square over 2 eta plus eta over 2 summation t1 to capital T vt square. So here we use the fact that w1 is 0 vector. Right, so when law is continuous, when we have this property, then vt is upper bounded by rho, and when we have b bounded property, then wt norm is bounded by b. That's it.